Today we'll be learning how to solve the navigation problem using two methods, the geometric method and the algebraic method. We'll first cover the prerequisite skills of geometric vectors for the geometric method and Cartesian vectors for the algebraic method before approaching to our navigation problem. For geometric vectors, we need to understand the law of sine and the law of cosine. By understanding the law of sine and law of cosine, we are able to know the relationship between the angle and the side length in the triangle. The law of sine tells us the ratio between an angle of a triangle and the side opposite to it is going to be constant in any angle of the triangle. For this triangle labeled here, it tells us that sine angle A is over the side opposite A, equals to the sine B over B, and equals to sine C over C. Law of cosine lets us find an unknown side of a triangle using two known sides of the same triangle and an angle opposite to the side we don't know. The formula of the law of cosine is a squared equals to b squared plus c squared minus 2bc times cosine A. We also need to understand the bearings, which are angles measured from the north point. Bearing can be in two forms, quadrant bearing and true bearing. Quadrant bearing divides the bearing by quarters. Measurement is read in respect with either north or south. Then the angle between either east or west. For example, this bearing reads south 30 degrees east. True bearing begins from the north point and encompasses an angle in a clockwise direction. For example, this angle just reads 210 degrees. Let's take note of some terminologies in navigation. In a flight problem, we have air velocity, which is the direction of an airplane's travel and speed, and wind velocity, which is the direction and speed of wind affecting the airplane's travel. And now that the prerequisite is out of the way, we can now solve the navigation problem. Here's an example. An airplane is flying at 750 kilometers on the heading of 50 degrees, and the wind is blowing at 60 kilometers per hour at a bearing of 120 degrees. What is the ground velocity and the direction of the airplane? Let's break it down part by part. First, we know about the speed and direction of the airplane. We also know the speed and direction of the wind. And we know vectors have no locations. We can form a head-to-tail triangle with this. Then we can find the resultant using the cosine method, which is the square root of 750 squared plus 60 squared minus 2 times 750 times 60 cosine 70 degrees, and resultant velocity equals to 731.7 kilometers per hour. Now that we have the velocity, next we will determine the direction of the airplane. We can find this by using sine rule, as we already know two magnitudes and one angle of the triangle. Angle beta inside the triangle is calculated as sine beta over 60 equals to sine 70 over 731.7. Therefore, beta equals to 4.42 degrees. Now we can get our final heading. So theta equals to our original angle minus beta, which equals to 45.6 degrees. Now that we know how to solve a navigation problem using the geometric method, next we'll solve by using the algebraic method. First, we need to understand Cartesian vectors. All vectors on a Cartesian plane start from the tail at the origin. Here we have a point P25. We make a position vector to the point, vector v25. Let's use the same example from the previous question. We know the airplane is traveling at a heading of 050 degrees, which is 50 degrees clockwise from the positive y-axis, equivalent to the angle of 40 degrees from the positive x-axis. Let the airplane velocity be labeled v. Do you remember your trigonometry of sine and cosine? Sine theta equals to opposite over hypotenuse, and cosine theta equals to adjacent over hypotenuse. Let's use these to find out our x and y coordinates. Vx equals to 750 sine 50 degrees and approximately equals to 574.5. Velocity y equals to 750 cosine 50 degrees and approximately equals to 482.1. Next, we want to find the velocity of wind. We'll label this vector w. We'll use the same method from the airplane velocity to find our x and y coordinates for wind velocity. Our magnitude equals 60 kilometers per hour, heading 120 degrees, which is 30 degrees to the negative x-axis. Therefore, Wx equals to negative 60 cosine 30 degrees, which equals to negative 51.96. And Wy equals to 60 sine 30 degrees, which equals to 30. Now let's find the resultant x and y coordinates. Rx equals to Vx plus Wx, which equals to 522.54. And Ry equals to Vy plus Wy, which equals to 512.1. Using Pythagoras' theorem, we can calculate the magnitude of the resultant. So, absolute value of r equals to square root of 522.54 squared plus 512.1 squared, which approximately equals to 731.6 kilometers per hour. Now let's find the heading using the trigonometry of tangent. Tan theta equals to opposite over adjacent. Let's do the working. Tan theta equals to Rx over Ry, which equals to 1.02. Theta equals to inverse tan of 1.02, which equals to 45.6 degrees. Therefore, the airplane is traveling at a velocity of 731.6 kilometers per hour with a bearing of 45.6 degrees, just about the same answer as we got from the geometric method. Now you know how to use a geometric method and an algebraic method to solve a flight problem. Hope you learned something from this, and thank you for watching.